So I know you still have some questions about the S and the P, but we'll just get through the end here and then we'll work it out. So in the Lewis model, we had the possibility for expanded octets with elements in the third row or larger, right? So phosphorus and sulfur, those guys. In valence bond theory, this corresponds to hybridization involving the d orbitals, okay? The energies of the 3d orbitals are similar to those of the 3s and the 3p. So you get your 3s and your 3p. And your 3d. And so if you look at something like, say, sulfur, and we see that sulfur has 6 valence electrons, right? 1, 2, 3, 4, 5, 6. But it can hybridize, and what that is we're expanding into these empty 3D orbitals. So in my hotel analogy, we've got electrons staying up here on the 3rd floor, and they're going to take up the 3s and the 3p rooms, and then if we have more electrons, they're going to go up to the 4th floor because that room's cheaper. But the differences in energy here are pretty small. And so if we need more orbitals, we can expand into this D room. The D room is there even though it's empty. So now when we remodel, we can do combinations of all 3 rooms. So we can take the S and all 3 of the p orbitals and then go into 1 or 2 d orbitals as well and mash them all together. So here we've got the 3s orbitals, the 3p orbitals, and the 3d orbitals. Those guys are empty, but they're there. And so we can combine S and 3Ps in one of the Ds, and then we call that sp3d, right? And so we have 5 orbitals that are the same, and then those unhybridized orbitals are sitting there. They were empty before, they're still empty. 5, we're going to get 5 orbitals that look kind of like this. Again, each of these lobes is 1 orbital. Its second little nubby lobe isn't shown. So AS5, the Lewis structure, we've got 5 single bonds around the arsenic. That's 5 electron groups. So sp3 will get us 4, but we need 1 more. So then we have to bring in D. And so we're going to get these hybrid orbitals here, 5 orbitals, and each of these can make a sigma bond with one of those p orbitals from the fluorine. So if we want to look at the electron diagram here, we've got sp3d, then there are 4 d orbitals that are just left. And so the 5 valence electrons from arsenic will each take their own bed here. And so for the fluorine, we're assuming fluorine does not hybridize. So fluorine's going to look like this. So, I should label that. This is fluorine, and this is arsenic. So each fluorine has 1 half-filled orbital. It can overlap with one of these hybrid orbitals on the arsenic. So here's a fluorine, half-filled orbital overlapping with one of those sp3d orbitals. And here's another fluorine, and another, and another, and another. Any questions? So I made 5 equivalent orbitals. They're going to have that kind of drumstick shape with a big end and a little end, right? And they're going to spread out in space as much as they can, just like the balloons did when we talked about Vesper theory. And so they're going to form this trigonal bipyramid shape. That's as far apart as they can get. So they'll be in that arrangement, and then each of these can overlap and make a bond with a fluorine. So each of these boxes here with one arrow is one of these sort of copper-colored things here. And then the green is this orbital from the fluorine that's half-filled. So fluorine's half-filled orbital overlaps with an sp3d. So this is overlapping with one fluorine, and each of these is going to overlap with a different fluorine atom. And so we're going to get 5 bonds. We have 5 fluorine atoms bonded to the arsenic. Yeah.
So this hybridization corresponds to the sublevel, like the amount of electrons that we can hold within each sublevel. So like in the P, you can only hold 6, right?
Mm-hmm.
Max. And in this case, we have 8 valence electrons bonding together. So we've already reached that P sublevel. We've already filled that P sublevel, so we need one more D bed. So that's why we take it, mash it with.
Yeah, in order to have an expanded octet, you need more than 4 orbitals.
Exactly.
Right. Because you get your half-filled orbitals and you overlap with another half-filled orbital, and then you get all your orbitals full. Well, the 4, sp3, will give you an octet. But here we need 10. So we need another bed. And so we're going to take it from that D room that's just sitting there empty anyway. Yes?
So why do we just take the last unpaired electron from fluorine and put it in the last group instead of
Well,
matching them with opposite spins?
I did it like this because they happen to line up nicer. So I have multiples of these, right? So here's another fluorine. You see how this could get tedious real fast. There's another fluorine, and that's going to form a bond with another one.
So the 5 bonds that fluorine makes with arsenic completes those 5.
Yep. So I have 5 hybrid orbitals that are half filled, and each of these interacts with one orbital from another atom and then results in a full orbital. A light went on over there. That's nice. Right, so then this is going to go to another fluorine and another fluorine and another fluorine. So 5 different fluorine atoms, and they each have this one half-filled orbital, and so they're going to bring that in, and they're going to overlap with the sp3d, and then they'll have it full. And so that's cool. They've got their octet, and arsenic is happy here because it gets all of its electrons paired up. Yeah. This is sp3d because I look at that and I see there were 5 electron groups. And so 1, 2, 3, 4, 5. I need 5 orbitals. So I start with the s and I go through the 3 p orbitals. That gives me 4, and I need 1 more.
And it won't go to sp4.
It can't go to sp4 because there's not another p orbital.
Oh yeah.
Yeah.
There's only 3 beds.
Yeah, so in the hotel, I need 5 beds that are equivalent for whatever reason. These guys are like, no, we each need our own bed, but we all need to be in the same room.
Because they're ready to mingle.
So yeah, we're going to have the girls over, and I don't know, that just gets weird. But so we'll take the S room and break down the wall, and then we've got the P room, and then we need to break down the wall and move it over a little bit to get one of those beds from the D room. S only has 1 bed. It holds 2 electrons. Yeah, so this is good. Some of these little misconceptions that really mess you up are getting straightened out here. Any other questions about this one? Well, what if we need a 6th bed in our room? So we can take the S room and the P room and take 2 of the beds from the D room. And then this is called SP3D2. And so we get 6 beds that are equivalent. We have 6 degenerate orbitals, and then these are left. They were empty before, they're still empty, they're just sitting there.
So the number of orbitals corresponds to the number of electrons per the number of beds.
When we've got single bonds, then we need the same number of hybrid orbitals as we have bonds. And so that's what we're seeing with these examples. So these 6 would do just like the 6 balloons and make this octahedral shape. So each of these purple balloon looking things is 1 hybrid orbital. It would probably have 1 electron in it, and then this could form a sigma bond with something else. So here's sulfur hexafluoride. So here we have the sp3d2. There's 6 hybrid orbitals from the sulfur, and they make that shape, octahedral, and then each of these can overlap with a half-filled orbital from the fluorine. Any questions? Do we need to recognize the shape of this? Well, we shouldn't have a problem with it because it's the same as the Vesper shapes that we already learned. And the shape of the molecule is going to correspond to the shape made by the hybrid orbitals. So how do we know, this is a question you've been asking me all morning, how do we know which hybridization scheme best describes the orbitals of a specific atom? Well, the rigorous method is you look at the degree and type of hybridization and you calculate it so that the molecule would have the lowest overall energy. We're not going to do that. We're going to go with good enough for Chem 1A. We're going to assign a hybridization scheme from the electron geometry of the interior atoms. It's not always correct, but in the problems I give you, it will be correct. So you're looking at number of electron groups. 2 groups, sp. 3 groups, sp2. You know, if I need 6, I don't have enough fingers. Right? You start with S, you count through the P's and into the D's, just however many you need. You need as many as you have electron groups. And these are the shapes. They're the same shapes as we saw for the geometries in Vesper theory. So 2 groups, 3 groups, 4, 5, 6, sp, sp2, sp3, sp3d, sp3d2. Yeah.
For electron groups, it's a single level of one. Is it also lone pairs?
Yes. A lone pair is also a group.
And then what about like a 2? Is that also a group? Or that's, like if it's just not like on this.
Well, there's lone pairs and then there's bonding pairs. You're either part of a bond or you're not.
But they're all groups.
They're all groups. Mm-hmm. So here are the instructions. You write the Lewis structure, use Vesper theory to predict the geometry, and that again comes down to how many electron groups. And that's how you predict the hybridization. And then, I'm not going to ever grade you on this, except for a little tiny bit on this worksheet. You sketch the molecule. You start with the interior atom and its orbitals, and then you show how it overlaps with the terminal atoms, and then you're going to label the bonds, sigma, pi, followed by the types of orbitals.
So we're not gonna-
Well, I'm not gonna ever grade you on your drawings. You should try to draw them, or at least draw them in your mind, because it really, really helps. It helps you to remember it. Okay, let's do this one. write a hybridization and bonding scheme for XeF4. So we have to start off with the Lewis structure. So xenon, and then we've got 4 fluorines, so we'll probably put those around. And then for electrons, I have 4 times 7 is 28, plus 8 is what, 36? Just a minute here. So for the bonds, I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 24, 26, 28, 30, 32. I need to put 4 more electrons. Can xenon expand its octet?
Yes.
Yeah. So I'm going to put those extra electrons as lone pairs on the xenon. So when I look at the xenon, how many groups of electrons does it have? 6 groups, right? So then my hybridization scheme is 1, 2, 3, 4, 5, 6. sp3d2, right? So 6 that's not what I wanted. 6 electron groups. I need 6 hybrid orbitals.
Because we got 12 electrons to
Yeah.
hybridize, right? Essentially.
So sp3d2. And you can't skip a p and leave it behind, right? So on the worksheet, what it has you do is it has you draw electron diagrams for the atom by itself and the atom hybridized. So for xenon, xenon has S and P, and it's got 8 valence electrons, right? Now, normally we wouldn't draw the d orbitals, but here, since we're going to be expanding into them, I think it's helpful to draw them. They're empty. So this is a xenon atom by itself. When I hybridize, I need 6, right? So I'm going to stick all 6 of those beds together in one room. I'm going to make all of these orbitals equivalent, degenerate. So for the hybrid orbitals, I'm going to draw 6 boxes. And that's sp3d2. There's sp3d2. And then the electrons, I'm going to stick in there, according to Hund's rule, separately at first, pair up if I have to. 1, 2, 3, 4, 5, 6. Now I have to pair up. 7, 8. These are the lone pairs. See, this one has 2 lone pairs. There's a lone pair and a lone pair. Those are the lone pairs on the central atom. And then left, I have 3 empty unhybridized d orbitals. On your worksheet, I'd like you to draw the empty d orbitals if they end up getting used, because however many boxes we start with, we should end up with the same number of boxes. Yes? I put 8 electrons in because xenon has 8 valence electrons.
So if the d orbitals don't get used, we just, or like the empty d orbitals that are there, we just draw them off to the side?
Yeah, just draw them off to the side. If your hybridization is only like sp3 or something, and D never shows up anywhere, then you could just leave all of them off. And the smaller ones like carbon, you're looking at the 2s and the 2p, and there is no 2d. That's why they can't expand. There's no more hallway. There's not another room to expand into. So this is the xenon hybridized. And then all of the fluorines are the same, so we don't really need to draw 4 of them. We could just look at 1. So we're not going to hybridize fluorine. So we look at fluorine. It's got S and P, and fluorine has 7 valence electrons. And so they'll go in there like that. Let's label this. This is fluorine. And then for the bonds that are forming, we're looking at what's going to overlap. The half-filled orbitals are going to overlap. So for fluorine, the only thing it can do is a p orbital. It's going to overlap a p orbital with one of these half-filled hybrid orbitals. And these are all going to do the same thing. We don't have any multiple bonds. And so the bond description there would just be, it's a sigma bond between xenon. What kind of an orbital is xenon using? sp3 d2, overlapping with fluorine, and fluorine is using a p orbital. That's the bond description. This is good enough for a hybridization scheme. You have to form a sigma bond first. The sigma bonds are always going to be lowest in energy because they're the strongest. The end-to-end overlap, that happens first. And then sometimes we have pi bonds forming. But here we can't have a pi bond forming because there aren't any unhybridized p orbitals on the xenon, and there aren't any. It would have to have 2 half-filled orbitals. And we look at this, and this is why fluorine only forms 1 bond, almost always. Any other questions? We did that one. CO2, is there anything after that? I'm losing my Wi-Fi again. Yeah, so let's just do CO2 real quick here. So I'll just fast forward to the Lewis structure. So here's carbon unhybridized. We have S, we have P, and we know carbon has 4 valence electrons, and they'd be in there like that. And then we're going to show how it hybridizes, and we're going to look at the central atom, the carbon, and say how many electron groups are there? There's 2. So I need an sp hybrid. I need 2 equivalent orbitals. So I'm going to put these together. So I've got S and P. That's an sp. And then I have left 2 unhybridized p orbitals. And then putting the 4 electrons in, because the energies are very similar, they're going to each have their own orbital. So this is the carbon hybridized. Okay? And then we have oxygens, right? So oxygen, we're not going to hybridize the oxygen. 6 valence electrons. Okay? 1, 2, 3, 4, 5, 6. Each oxygen is the same. Since we have the space, I'm just going to draw the other one as well. So here's another oxygen. The bonding scheme is how can we overlap these half-filled orbitals? And the Lewis structure gives us hints about what to do. I need a bond, well, 2 bonds actually, between carbon and 1 oxygen, and 2 bonds between carbon and the other oxygen. I have to have a sigma bond with each first. So I can make a sigma bond with my hybrid orbital, and it's going to overlap with 1 p orbital from an oxygen. And then the other oxygen is going to overlap with the other p orbital. And then, so those are sigma bonds, and then I have an unhybridized p orbital, and here's another p orbital, and then on my carbon I have 2 unhybridized p orbitals. So those could make pi bonds with each other. So I can make a pi bond here and a pi bond here. The pi bonds are between carbon and oxygen, right? Between carbon and oxygen. And the electrons, the orbitals being used there are p on the carbon and p on the oxygen. For the sigma bond, you see that okay? That's kind of dark yellow. These are the sigma bonds. I'm going between carbon and oxygen. On the carbon, I'm using the hybrid orbital, sp, and on the oxygen, I'm using a p orbital. Yes? For pi bonds, it's always just plain old p orbitals. P orbitals for pi bonds. Use the hybrid orbitals for sigma bonds. So that's, I'm gonna take 1 for each oxygen. I can't use both of these with 1 oxygen because these are at right angles to each other and these are on opposite sides, and it just doesn't work out. That's where drawing a picture can help. But any questions? Yeah, I only wrote out 2. There are 2 kinds of bonds. We're not going to worry about how many of them there are. Any other questions?